speaker is John Watt, who is in the Center for Integrated Nanotechnologies at Los Alamos. And the title of John's talk today is Soft Matter and Nanomaterials Characterization by Cryogenic Transmission Electron Microscopy. So over to you, John.
My name is John Watt from the Center for Integrated Nanotechnologies at Los Alamos National Laboratory, and it is my pleasure to give this MRS webinar today on soft matter and nanomaterials characterization by cryogenic transmission electron microscopy. So soft matter and nanomaterials present a wide range of different material species and can include biological soft nanoparticles, for example, viruses and their polymer conjugates, synthetic organic nanostructures, so typically we think about polymers, supramolecular materials, which are architectures consisting of molecules that are able to self-assemble into larger constructs, so for example, metal organic frameworks, and inorganic nanoparticle colloids, which typically have a soft corona consisting of an organic ligand molecule, which gives stability in solution. So soft matter has historically been an unlikely candidate for investigation by electron microscopy techniques. This is due to damage by the electron beam, as well as an inherent instability under a high vacuum environment. Preparation for TEM also typically involves drying on a thin carbon grid, which yields two main limitations in the imaging of soft materials. One, it introduces drying artifacts, which is especially significant for characterizing hydrated structures. And two, there is now a low contrast difference between the carbon-based structure and the carbon film on the TEM grid. This can be solved by negative staining, for example with uranyl acetate, which gives the carbon sample a white color against the black background of the grid. But this can introduce significant swelling to the structure, again introducing artifacts and uncertainty. So characterization of soft matter has typically relied on ensemble scattering techniques, such as dynamic light scattering and small angle X-ray scattering. However, these techniques are model-based and only give statistically averaged information on the ensemble. The recent development of cryogenic transmission electron microscopy, or cryo-TEM, is providing the soft matter community with an exciting opportunity to probe the structure of these soft materials in real space. Cryo-TEM reduces electron beam damage and allows for characterization in a native, frozen, and hydrated or solvated state, providing direct visual representation of the soft structure. So by imaging against a background of vitreous ice, not only do we get an image of the hydrated structure, but we also see an increase in contrast difference when compared to depositing on a carbon substrate. This is in comparison to another in situ electron microscopy technique, which is liquid cell TEM. So this is a powerful tool for capturing the dynamics of the particle system, and so it's being limited for soft matter originally caused by the increased electron path length through the liquid and coupled with typical low contrast. Liquid cell TEM is also limited in probing materials interfaces due to sample movement under the beam. So today I'd like to focus on two classes of materials in particular, synthetic organic nanostructures, so specifically polymers, and inorganic nanomaterials. And I'll give an example on how cryo-EM is helping to solve questions in nanoparticle chemistry. So first I'll begin with synthetic organic nanostructures. So here we're talking about polymers. So in imaging polymers using TEM, damage by the electron beam is still a definite factor. However, they can survive under a high vacuum environment. And as such, room temperature scanning electron microscopy, SEM, and room temperature TEM were useful in the early understanding of a system of polymers called block copolymers. So here, as early as 1966, researchers observed an ordered structure in styrene butadiene block copolymers, and they identified that the periodicity of these lines was correlated with the molecular weight of the polymer blocks. Then in 1988, the 3D microdomain morphology of a polystyrene polyisoprene block copolymer was imaged using bright field TEM on an electron transparent sample. So here they carried out negative staining selectively on one of the polymer blocks, and you're able to get that contrast difference, and this matched well to early computer simulated predictions. So while providing good insight, these structures are bulk and stable at room temperature, but polymer science also produces higher order architectures that can be hydrated or solvated and dispersed in solution. And so this requires novel characterization techniques, since preparing for conventional TEM will introduce artifacts, hence cryo-EM. So some of the earliest examples of cryo-TEM on hydrated or solvated synthetic organic nanostructures was focused on triphasic surfactant, oil, and water mixtures. So surfactants in these conditions assemble into a variety of microstructures, including micelles, microemulsions, vesicles, and liquid crystal structures, as shown here by an early rich ternary phase diagram. And such systems are of biological and technological importance, for example, in catalysis, drug delivery, purification techniques, and in nanomaterial synthesis and integration. So these types of structures suffer greatly from drying effects when preparing for TEM, so being able to image them in their native hydrated state would provide real space information that can also be used to constrain scattering models, so you can use the two techniques to converge towards a full understanding of the material structure. So as early as 1991, there was reported a cryo-TEM image of 1 weight % CTAB micelles swollen and tolerating, albeit a rather low magnification. In the recent literature, we see the evolution of cryo-EM for soft matter analysis to these beautiful images of hydrated structures with good contrast against the vitreous ice background. So reported have been liposomes interfaced with citrate stabilized gold nanoparticles, cross-linked nanobubbles of pure perfluorocarbon, and mixed block copolymers grafted to the surface of silica nanoparticles. So these images also show how crucial cryo-EM is in probing the inorganic-organic interface, as the soft matter can be locked in place and given good contrast. We can also see how the improvement in resolution and sample preparation techniques is allowing researchers to identify even more exciting features about these types of systems. So cryo-EM can be used to capture a snapshot of dynamics and structural transitions in soft matter. So here the authors investigate biocompatible non-ionic surfactant solutions and their evolution from spherical micelles into nano and micro-sized branch networks and ultimately crystal-like structures under a simple combination of temperature and flow conditions. So they use cryo-TEM to observe a two-step process when the system is cooled to just below room temperature. In the first image here, we see a snapshot of a structural transition from spherical micelles to worm-like micelles, with a transition area clearly defined here between the two dashed lines. In the second image, they observe a transition to branch-like structures which were identified as micellar bundles. And interestingly, this behavior was reversible, with the spherical micelles reappearing when the system was returned to room temperature. So conventional microscopy gives you a 2D projection of a three-dimensional structure. However, the microscopist now has cryo-electron tomography in their toolbox, which yields greater detail for 3D structures, including things like self-assembled structures. So because we are freezing the sample, we can also now probe 3D structures in both equilibrium states and during dynamic changes. So cryo-electron tomography involves the collection of a series of 2D cryo-TEM images taken at different tilt angles, often up to plus or minus 70 degrees. The images are then reconstructed to give a 3D representation of the sample called a tomogram, which represents the density within the particles. So here we have an example where the authors reveal hidden structural features in multi-compartment micelles using cryo-electron tomography, which would not have been observed using either conventional TEM or indeed with 2D cryo-TEM alone. So they first form multi-compartment micelles from triblock turb polymers in an aqueous media. They then complex the excess PMMA with a second diblock copolymer, which yields a charged corona around the particle, capable of coordinating with a target species in solution. For example, to immobilize inorganic or organic nanoparticles or proteins and enzymes. So cryo-TEM was used to identify the structure at each step, but of course here we are looking at a 2D projection. By carrying out a tilt series and 3D reconstruction, the authors were able to observe a rather surprising structure that consisted of a complex arrangement of vertical lamella. The structure kind of resembles a wind turbine, with the lamella becoming more bent as they project away from the particle core. And all of this would not have been discernible from the 2D projection. So with cryo-ET, because now you are taking multiple images on a single structure, control over the electron dose is important. This is in order to reduce sample damage throughout the tilt series and to ensure that artifacts are not introduced into the system. So in materials science, there are a large number of systems that are dispersed in organic solvents and not dispersed in aqueous solutions. Therefore, developing cryo-TEM techniques to allow for sample preparation and imaging in organic solvents is set to have a significant impact on materials science. So here we have poly-3-hexylthiophene, which is a promising component in solar cells and is exciting as a cost-effective choice for large-scale production. Its development relies on printing technologies, which includes inks, and therefore understanding the behavior of these inks is crucial for effective manufacturing. So aggregation of the conducting polymers in the ink solution has long been blamed for anomalous behavior, with strong intermolecular interactions such as pi stacking being a common explanation for the aggregation. As these inks are dispersed in volatile organic solvents, traditional characterization techniques, conventional TEM, can introduce artifacts via drying. But now we're having cryo-TEM sample preparation techniques mature to a point where automatic vitrification robots like the Vitrobot that have atmospheric and temperature control can be modified to vitrify organic solvents. So this is opening up the real possibility of organic solvent cryo-TEM. So here, researchers at the Eindhoven University of Technology successfully observed P3HT nanowires vitrified in both orthodichlorobenzene and toluene. They performed both 2D cryo-TEM and electron cryotomography that revealed 1.7 nanometer space lamella composed of pi-pi stacked conjugate backbones of the P3HT along the length of the nanowire, diffuse edges in one direction and sharp edges on the other. And this is originating from different degrees of ordering within the P3HT crystal. So now I'd like to shift gears and discuss inorganic nanomaterials, and in particular an area where cryo-TEM has been able to answer questions not possible with conventional TEM and scattering techniques. So many of the applications of magnetic nanoparticles rely on the detection of their relaxation dynamics when an applied magnetic field is removed. This has recently been demonstrated to be useful in cancer detection using magnetite nanoparticles coated in cancer-specific antibodies. So magnetic nanoparticles relax via two distinct mechanisms. If the nanoparticles are dispersed in solution, they are free to relax via rapid Brownian motion. However, if the nanoparticle is attached to a cancer cell via the selected antibody, it can no longer reorient in space, and the magnetic vector is forced to relax via the slower nail relaxation mechanism, which can now be detected using sensitive squid detectors. So to detect the cell, we introduce the magnetic nanoparticles, and we have a population which attach to the cell of interest. We align the particles in a magnetic field and then switch that field off. We wait a short time, around 35 milliseconds, to allow those unattached nanoparticles to relax via the fast Brownian mechanism, and then we start the detection of those nanoparticles that are relaxing via nail. And this gives us a good indication of the size and location of the cancer. If we look at the formula for nail relaxation, we can see that it is strongly dependent on nanoparticle size, so it's proportional to the exponential of the volume. Therefore, to ensure all the nanoparticles are relaxing in a similar time window for effective measurement, we have to have incredibly tight control over nanoparticle size. So we've shown that we can achieve this and synthesize magnetite nanoparticles, Fe3O4, anywhere from 9 up to 35 nanometers in size, with a consistent coefficient of variation of around 6%. So these have a very strong magnetization, 70 amp per meter squared per kilogram, which approaches that of bulk magnetite. However, interestingly, when we look at these via small angle X-ray scattering, we see some deviation from the model fit for a non-interacting sphere, and this is indicative of particle interactions. So why is this important? Well, now we introduce a second term into the formula for narrow relaxation, which will significantly affect the relaxation time. So now we've done all that work to make the nanoparticles very tight size distribution. We also need to understand in a very clear manner exactly how they're interacting in solution. So small angle neutron scattering experiments revealed some interesting observations. So these were particles that were dispersed in water by surrounding in a hydrophilic polymer layer. And small angle neutron scattering experiments showed that there was about 81% volume fraction of dimers, and some also existing as trimers, as well as monomers. So if we were to investigate this using conventional TEM, what we would do is we would take a nanoparticle solution, we would drop cast onto a carbon grid, and then we would look at that grid under the TEM. So you may identify some of these types of structures where this looks like a dimer. Here we may have a line of nanoparticles. Here we may have two dimers coming together. But this is not always observed, and this is because we now have drying artifacts introduced to the system. And also drying effects can change the strength of magnetic interactions as the capping ligand desolvates upon drying. We can look to negative stain experiments. So this is staining using uranyl acetate to increase the contrast of the shell against the carbon background. But again, we're introducing artifacts to the system. So here we observe a trimer and a dimer, but we cannot be sure that this is not due to drying effects. So then we turn to cryo-EM. So this is a solution of those hydrophilic polymer magnetite nanoparticles dispersed in water. We plunge freeze and look at them on the cryo-EM against a vitreous ice background, and we do indeed observe some of these higher order assemblies that the small angle neutron scattering experiments thought were there. And we do observe some magnetic dimers, and of course we do observe some formation of chains. So this is an example where cryo-TEM has confirmed the observations from ensemble scattering techniques, and the thing to understand here is that this would not have been possible with conventional TEM. And I thank you for your attention.
Thank you, John, for that excellent talk. And we're now going to open up for some questions that have been coming in from the audience in the webinar. So the first question is, which organic solvents are suitable for cryo-EM? And could you also elaborate on any modifications that are necessary to the Vitrobot robot that you described that are necessary in order to make it compatible with organic solvents?
So yeah, in terms of choosing the solvent, when we think about water and its stability under the beam when it's vitrified, you know, we have hydrogen bonding there, which can give it some stability. So we kind of need to substitute that for something else when we look to organics. And here, kind of pi-pi stacking is your friend. So things like toluene, benzene, dichlorobenzene, where you can get some advantage of that pi-pi stability under the beam will give you a lot of help. So things like hexanes and unfortunately chloroform are not as good. In terms of modifying the Vitrobot, excuse me, really depends on how adventurous you want to be. So it's about identifying the parts in there that could be attacked by the solvents. So there's the humidifier, which obviously contains a lot of solvent, and then replacing those for things like Teflon. So it's a little bit of a Frankenstein effort, but I think it can be done.
Excellent. Okay. And then you talked quite a bit about using cryo-electron tomography, and of course, that is really a very much a developing field for our colleagues on the life sciences side. But most of their work has really been driven and has achieved the results using what they would call single particle methods. And do you think that the single particle reconstruction methods used in the life sciences have a real application in material science?
Yeah, so this is an interesting question because I think, a lot of time in materials, especially nanoparticles, we have a finite size and shape distribution, and, that's one of the things we're always trying to do is tighten that up. So for these single particle reconstruction techniques to be applied to soft materials or nanomaterials, we need a very high quality ensemble with a tight size and shape distribution. So experimentally, this is quite difficult to achieve, even with the kind of highest quality biomimetic materials. However, there has been some examples of applying cryoelectron tomography to a single nanoparticle or a single entity to kind of get that 3D surface structure. But here you have to be very careful about electron dose, because you're dosing one entity throughout the tilt series, and so it's very easy to introduce artifacts.
Okay. Moving to the next question, there's a question that really relates to the role of cryo-TEM for people studying structural alloys, metals in general, and in particular how it could be combined with in situ deformation experiments. So the question relates to, how challenged would that be in terms of, the limited field of view, the temperatures that could be achieved, and whether you could actually combine in situ mechanical testing with cryo-EM.
Right. So yeah, this is a really interesting question, and it's great seeing kind of all of these things in TEM that have been done in heating. Deformation, looking at surface phase change, looking at phase changes and things. Now these questions are starting to be asked, below freezing, which I think is really exciting. So, this really comes down to the holder. So, can you take a nano indenter holder and then add a dewar to the back of it so that you can cool? And that's really where these kinds of experiments will be able to be done. I think the minimum temperature to go down to is obviously LN2 temperature. And getting control between freezing and LN2, I think, is going to be a really exciting thing to see what these holder manufacturers can do in the future. In terms of field of view, the great thing about some of these new direct electron detection cameras is their wide field of view. So compared to kind of using a CMOS camera, now we're able to look at a large ensemble of particles, or in the field of metallurgy, you're looking at quite a large area. You're able to kind of set off your experiment, and then later on you can look for those regions of interest where things have occurred, and so you can start now to think about kind of statistically relevant information coming out of the TEM, which I think is just a super exciting development. Absolutely.
So we've got a few questions coming in that are relating cryo-TEM versus cryo-STEM. Are there any specific considerations you need to take into account comparing one to the other?
So I have limited kind of experience with cryo-STEM, but that's something that we're really interested in trying, and I think it just comes down to dose rate. So just the same as, when you're doing conventional STEM, you have to have a very nice clean sample so that you don't get burning of the carbon. I think, considering dose rate is going to be even more important for cryo-STEM, because you don't want to burn away your vitreous ice background. So, I think it's a case of, finding a region or a test sample where you can figure out your dose rate so that the vitreous ice survives, and then going back and finding your region of interest and performing the experiment there.
Okay, and that probably relates to another question that's someone else has submitted here, which are relating that to the possibilities and challenges for doing elemental analysis during cryo-EM, because in most cases these days when we do think about elemental analysis, we'd be doing that in STEM mode. So could you give some comments on the possibility of doing analytical work in cryo-STEM beyond the issues of damage?
Yeah, so it has been done. I guess it's finding the most sensitive detectors that you have access to. But yeah, in terms of kind of other considerations, I'm not too sure about that one right now, unfortunately. I think this is one of those techniques which has just been developed, and so we're all kind of learning as we go.
Yeah, absolutely. I don't think we're looking for, as you mentioned already, developments in terms of holder technology, and certainly if we want to avoid stray signals from an X-ray detector, then there's a lot of design elements that would need to go into holder design and lens design as well.
Right, and considering drift, and then also making sure that your vitreous ice background is very clean and clear of any contaminants, so that you're not getting stray signal from that, because now you don't just have a carbon film which the composition of.
Yeah, indeed. And that actually leads quite nice. So there's a few people have been asking, are relatively new to the technique, and are asking just how is the cryo environment achieved and maintained?
Yeah, so that's a tricky one. I mean, the quick answer is plunge freezing your medium into liquid ethane, which is that's led to the development of the thing called the Vitrobot, which is the Thermo Fisher tool, but there are tools from different companies as well. And then once you have it plunge frozen, then it's about doing all of your work under liquid nitrogen to maintain that vitreous ice background. And there's two things you want to do. Is one, not let it go above the phase change to crystalline ice, which is about minus 137, 138 Celsius. And the other one is obviously you don't want it to melt. So there are a number of things that are provided by vendors of TEMs and plunge freezers, transfer stations and things like that. But at the end of the day, you have to be very careful, very meticulous in terms of loading the sample onto the TEM. It's trickier when you have a TEM that is room temperature. Some TEMs come equipped with what they call a cryo box, and so this is an LN2 cooled kind of box that goes around the pole piece. So now you're putting a cold holder into a cold TEM, which increases success. So there are a number of different manipulation steps, all done under LN2, and it's just about kind of being careful and trying to be efficient with the transfer.
Absolutely. Again, one of the things that in structural biology they worry about greatly is the thickness of the ice, and that question has come up from one of the participants here asking, is the restriction of ice thickness a concern when you're studying 3D assemblies? Yeah,
absolutely. So, if you're wanting to do something like tomography, then now geometry becomes important, right? Because you're tilting, and so you have to have the right grids that give you enough space, the right holder to give you enough space, so that when you tilt to high angles, you're not, clipping the edge of a grid bar or something like that. And then, this question is very relevant, that the thickness of your ice becomes very important, because if you're, often in the grid, the thickness of the ice will be more on the outsides towards the grid bar. So you want to be looking at a sample that's in the middle where you have a nice thin layer.
Okay. And again, a sort of related question is, do you encounter problems with differential thermal expansion properties between the particles and the liquid? Someone was wondering about here.
Yeah, I think that's definitely a consideration, especially in the freezing. So you want very high freezing rates, and I think that can be a consideration. Say if the thermal transport of your sample is not fast enough or something, and then I think that would be a consideration under the beam as well, making sure that you don't preferentially heat your sample with the beam or something that will give you kind of localized melting around it. But, again, this will come down to being sample and material specific, and it's about kind of iterating your conditions until you find the ones that work for your sample.
Yeah. And when you talked earlier about, the issues of electron beam damage, whether it's on the ice or on the sample. How do the electron doses that you're employing in your work compare with the kind of doses that people are using in structural biology and cryo-EM?
You know what? I don't think I could give you a value for that. But what I can say is that, with the use of these direct electron detection cameras like the K3 and the K2, we are pushing the dose rates for those cameras kind of, to their limits, to what they can do. And I think, probably in the biological space, they're doing that as well.
Yeah. I'm just reading this question. And then there is a question of what type of temperature control and range is currently possible
with cryo. So this goes back to what I was saying before about, now some of these kind of phase change questions and, structural questions that people have been asking at high temperatures. Now it's at low temperature. So at least what I'm aware of and what we have installed is that, it's a binary temperature control. We have room temperature and then we cool down to LN2 temperatures. There is the idea that maybe you could let the holder kind of warm up passively and you could look for some change, but you have a lot of drift in the TM when that's happening. So what I think is really exciting is, if we can start to control at these lower temperatures, say minus 100 C, can we do that in the TEM? And if anybody has any idea how to do that or a holder, then I'm very willing to hear. Yeah.
I can actually add just a little bit to that because I know a couple places are having the very initial cryo holders that can do those intermediate temperatures. And I think on arXiv, there's the very first paper showing one of these, the stability that these can achieve now. Basically what they do is they use a similar design except for the very tip, and the tip has a little MEMS chip on it that can be heated locally. So you heat the entire holder and that can become stable that way, and then they use the MEMS chip to heat very locally to some intermediate temperature between room temperature and cryo. And that apparently can also be very stable even down to atomic resolution.
Oh, very cool, very cool.
Yep.
Who's the author of that paper?
That's from Lena Kirkudis' group at Cornell.
Oh, okay. Fantastic.
Great. And then I think we got through almost all the questions here. There's one more that's come in that's slightly off topic, but it's really relating to magnetic materials and in some ways how safe it is to put magnetic materials in the microscope in electromagnetic lens. But I imagine the person's imagining that they're going to look at the magnetic materials as a function of temperature and look at the magnetic phase transformations. Do you want to comment on that, Judd?
Well, we put iron nanoparticles in there all the time, and I've never seen one fly off to the objective, although maybe it did before I saw it. So you can do things like Lorentz microscopy on magnetic materials where you actually turn off the objective lens. We also have a plasma cleaner in our TEM, which we use regularly. That's a tricky one.
Yeah, I think maybe I would add in for that participant is that in the past when we used to by electropolishing or dimpling, we'd make 3 millimeter discs of magnetic material. Then you were putting a reasonable amount of magnetic material into your lens, and if it wasn't held securely in the holder, then yes, you could create problems. But these days, if we're looking at nanoparticles or if we're making samples with a focused ion beam, the actual sample is really very small, and so it's much less of an issue than it was perhaps previously.
And I would say that if it's not secure enough to not fly off into the objective lens, then it might fall off as you're putting the holder in anyway. So it should probably be more secure.
Yeah, absolutely. Okay, John, I think we covered all of the questions for the moment. So okay. if that's, I think we could then